All right, so I think we can start. Yeah, I just pressed record.
Okay.
All right. Hello, everyone. Welcome to this week's reading group. I guess it's probably a slightly bigger audience than usual. That's the joy of Zoom and online meetings. So we're very happy to have Nikunj Saunshi from Princeton. He's a PhD student advised by Sanjeev Arora. He's done some really cool stuff on word embeddings and contrastive learning. And today he's going to tell us about some very recent work on some sample complexity separations and meta-learning between the convex and non-convex case. Just the ground rules, I guess. Keep yourself muted. If you have a question, raise your hand. The raise hand button is somewhere. If you put on manage participants, there's a little button that kind of looks like a raised hand. If Nikunj isn't hearing you, I guess unmute yourself and ask a question. And otherwise, yeah, Nikunj, take it away.
Yep. Thanks for inviting me, Andre, and thank you all for coming to the talk. So as Andre said, I'm going to be presenting some recent work on sample complexity of meta-learning, especially initialization based meta-learning methods in the convex versus non-convex settings. And this is joint work with Yi Zhang, who's also a grad student at Princeton, advised by Sanjeev, Misha Kodak, who's actually a grad student at CMU, and probably in the audience, and Sanjeev Arora, who's my advisor. Okay, so what is meta-learning? In the simplest form, you can think of it as having access to some training tasks. Let's say you have demonstrations for riding a bike or a bicycle or a car. And the goal is to summarize these training tasks into a learning algorithm that can be used to solve a new task. And hopefully the new task can be solved with fewer samples. So if you get demonstrations for how to ride an aeroplane, you hope that this algorithm can help you succeed at that task. Some very closely related problems are those of transfer learning, learning to learn, and multitask learning. And in this talk, I will be presenting perhaps a narrower view of meta-learning that's more relevant to this talk. So if I miss some components of meta-learning, please forgive me. Okay, so some more concrete examples on meta-learning problems. One of them could be predicting the next word on the phone keyboard. And here different tasks could correspond to different users. So you won't have the exact same prediction model for different users. You might want to adjust it based on their preferences. And maybe you would want to predict the probability of a patient having a disease given an X-ray image, and the different tasks could be different regions or different countries, different hospitals. And of course, our favorite problem of self-driving cars, where tasks could correspond to different environments. And basically, most machine learning problems can be made into a meta-learning problem, be it supervised, unsupervised, or reinforcement learning. So hopefully you're convinced that meta-learning is an important problem. However, for meta-learning to be useful, you need to assume that the tasks are related in some way. Or in other words, it should be the case that solving the training task should indeed be useful to be able to solve a new test task. And the goal is to use some notion of task similarity in order to show the benefit of using training tasks to reduce the sample complexity of a new task. And when I say reduce, I'm comparing it to the sample complexity of learning the new task from scratch without access to any training tasks. And in the following slides, I'll describe a popular formalization for meta-learning and define what sample complexity means in this setting. And also we'll see how some intuitive notions of task similarity measures show up in these notions of, these definitions of sample complexity. Also, as Andre said, feel free to stop me at any point and ask questions because there might be a few notations, but I'm going to try to develop them sequentially. So if you have any questions about any notations or anything, please stop me right away. Okay, and for the rest of the talk, we're going to assume that, there is another connection between the tasks. The train and the test tasks are basically going to be IID samples from some underlying distribution over tasks. Note that this is not the only interesting setting in meta-learning. In fact, there has been work on online meta-learning empirically and in theory, and there are some guarantees for convex losses or even not necessarily convex losses, but sometimes they're infeasible algorithms. But that's not going to be the focus of this talk. We're going to focus on this distributional setting. Okay, so now I'll first give a formulation for meta learning, describe what I mean by initialization-based meta learning methods, and instantiate that framework in the case of existing convex losses, guarantees for convex losses. Okay, so we first define a task in meta learning, and that's defined as a distribution over some domain Z. And let big theta be a class of model parameters that one wishes to learn. So for example, you can think of theta as the parameters of a neural network, the weights of a neural network. And we define the risk for certain parameters theta on the task T to be the usual notion of average loss on a point Z that's sampled from this distribution T. So I'm going to use notations by denoting the task and the distribution it corresponds to as T. And standard settings include the loss function could be the 0-1 loss, which is the case of classification, or you could also have a regression problem where you have the squared error loss. And note that the function f here is going to be the prediction function that you're going to learn. So you can think of f as being a neural f as being the output of a neural network, theta as being the parameters of the network, and x being the input to the network. And again, in this talk, we are going to focus on the regression setting. Okay, so now since we are in meta learning, we also have a distribution over tasks, and we call this distribution mu. And formally, the problem of meta learning can be seen as given access to tasks T1 up to T capital N that are sampled from mu. The goal of a meta learner is to output an algorithm where this algorithm is going to take as input a data set of size n that would be given for a new task. And using that data set, it's going to output certain parameters from this class big theta. And the performance of an algorithm returned by some meta learner is going to be measured by this notion of average and excess risk. So for an algorithm, we define the average risk as the expected loss over first sampling a task T from this distribution mu, and then sampling a data set of size n for this task, and measuring the task risk of the output of the algorithm when given this data set S. So the two important points to note are that we are measuring the performance on the average task, which is on a newly sampled task, and the algorithm will only have access to n samples from the new task. And note that this alg is going to be the output of what the meta learner is going to return. And using this, we can define the excess risk, which is we just subtract away from the average risk this quantity R star, which is the best possible performance you can get from this class big theta. So you just subtract away the expected best possible loss that this class can achieve on that particular task. And this framework was introduced by Jonathan Baxter in this seminal work on the model for inductive bias, and has been subsequently adopted by many recent works.
And Nikunj, are you going to care how many samples you have from the capital N, like tasks tau 1 through tau n?
Yes, yeah, just getting to that.
Oh, okay.
So yeah, so using this framework, the guarantees are at a very high level, very vaguely going to look of the following form, which is given access to these n capital N tasks with perhaps small n samples per task. The excess risk for the output of the meta learner is going to be upper bounded by some notion of the complexity of the tasks, perhaps measured with respect to the model parameter, the parameter class big theta, divided by some notion of the total number of tasks and the samples per task that you get, plus some notion of the similarity between the tasks divided by the number of samples n that you get for a new task. Now, this is a very high level view of what the bounds look like. And note that I've put this n here in the red because so this n is the number of samples per training task, and this could be different from this n. There are different bounds where the dependence on the capital N and small n are slightly different. Sometimes they show up in the square root, sometimes they don't show up at all.
Sorry, I have a question. This looks like as the similarity between the tasks increases, the bound gets worse, or is like you have a term in the upper bound task similarity that seems opposite?
Right, that's a good question. Maybe task similarity is the wrong term, the wrong word to use there. Think of this as like that's some inverse task similarity. So the more similar the tasks are, the smaller that bound is going to be.
Okay, yeah.
Yeah. So the hope is, as was pointed out, that if the tasks are more similar, the total samples you need for a new task, small n, only needs to learn the underlying similarity between the tasks and not suffer the complexity of each individual task itself. Okay. And in this talk, we are mostly focusing on the second term, which I'll be referring to as a new task sample complexity. So what's the dependence, like how many samples do you need for a new task? And like what notions of task similarity measures will give us reduction in sample complexity for a new task? While the first term is also important, which is a question of how many training tasks and how many samples per training task you need, and is also an active area of research, I won't be focusing on that in this talk. So I hope that answers your question, Andre.
Yep.
Okay. So any questions on this framework and the notion of excess risk, because this is going to show up all through the rest of the talk.
So I guess you're going to eventually restrict what the algorithm is allowed to do, right? Like you haven't got to that point yet. Okay.
Right. And I think, yeah, that's the next slide basically. So now I'm going to describe what are initialization-based meta-learning methods and basically what are the kinds of algorithms that a meta-learner is allowed to output. So these kind of methods were popularized by this paper by Chelsea Finn and colleagues in 2017 called MAMMAL. So it stands for Model Agnostic Meta-Learning. And the high-level idea in these methods is that you want to learn using the training tasks a good initialization for the model parameters, such that for a new task, you can use the samples to just fine-tune the network from that good initialization. So in this figure, for example, you can think of this as being a good initialization for the model parameters. And these are the optimal parameters for, let's say, 3 different tasks. And this initialization is in some sense close to these parameters. So you can see the pointer, right, on the screen?
Yeah.
Yes. Yes.
Okay, thanks. Yes. So, and intuitively, you would rather learn an initialization like this than, let's say, some initialization here, which is far away from all of these optimal task parameters. And based on these intuitions, they came up with an algorithm, and I'll describe one such algorithm later. But the biggest feature of these algorithms is that the training tasks are used to only return an initialization, theta in it. And the algorithm that you'll use for a new task is going to take samples from it and run some kind of gradient-based method on the empirical loss, starting from this initialization theta in it. And instead of starting from a random in it, you're going to use this meta-learned theta in it and hope that now you require fewer samples. So I think this should answer Andre's question about what are the restrictions on the algorithms that a meta-learner can return.
Actually, maybe a quick question about how you should think of this as opposed to maybe things like representation learning for transfer learning. Like, so when you have something like representation learning, I guess your goal is to learn some kind of representation that maybe you can train a simple classifier on top of, like maybe like a linear classifier or something. And here, I guess your notion is slightly different in the sense that you want a point from which you can do like a simple algorithm, maybe simple being captured by like a few gradient steps. So is there, I guess, like, should I think of one of these tasks as being easier than another one, or like incomparable, or how should I think of these?
Right, so that's a good question. So in some sense, you can think of representation learning as also an instantiation of this, though I would not exactly that, but for example, you can think of the weights of the neural network that are, so in representation learning, you basically learn, let's say, everything up to the second last layer using multiple tasks, and then the penultimate layer basically gives you good representations. And for a new task, you just fix that representation and you learn the linear classifier over those representations. And you can think of that also as learning and initialization for the entire network, which is learning the representation for the first, like, let's say L-1 layers, and learning, let's say, zero initial or random initialization for the final layer. And for a new task, you're only going to update the final layer. So in some sense, it can be seen as an instantiation of this.
Right, though I suspect here you will allow, like, I guess you will require a small amount of gradient steps. And in principle, if you're fine tuning a linear classifier on top, like, you could presumably do like many steps, and what you're restricting is the fact that like you only train the last layer, right? So maybe it's like a different kind of restriction.
Right, but like later on, the guarantees that we will show are all going to be of the form where you just update the final layer, even though you can update all the layers. But you can just think of, like, instead of a few steps, you can always think of doing some like gradient descent on some regularized objective on the final
Gotcha,
layer.
gotcha. Cool, thanks.
Yeah, good question. Okay, and of course, like, we are studying these methods because they have been they are very popular and have had successes in multiple domains, and like not just supervised learning, but also in reinforcement learning. And mainly because they are model agnostic, in the sense that you don't care about what, let's say, what kind of neural network you're using to learn this, as long as it's differentiable and you can pass do gradient updates efficiently, you can backprop easily, you can use any of these methods because they just rely on gradients. And there are, since mammal, there have been other variants of this, like first order mammal, reptile, etc. And in the next slide, I'm going to describe the algorithm reptile that's going to be most relevant for this talk. Okay, so I'll describe how this algorithm reptile, which was introduced by Nicole et al. In 2018, how it learns initialization. So I'll just set up some notation for it. So let GD of T and theta in it be the output of running gradient descent on the loss LT starting from theta in it. I'm sorry, I missed the starting from theta in it part there. And also we're going to denote like T hat as the empirical distribution for a task T. So if you're given a data set of with n samples for a task, the uniform distribution of those samples is T hat. And now given access to these capital N tasks, the reptile algorithm does the following. So it starts with some initialization, let's say either random initialization or, yeah, let's say random initialization, theta 0, and iteratively updates this initialization by doing the following. So it basically does this interpolation step between the current initialization and the output of running gradient descent on this empirical distribution for the task I+1. Importantly, you run the gradient descent algorithm starting from theta I. So in this figure, you can see that basically you're at this point theta I right now, and you see a new task Ti+1. So you run gradient descent on this loss on this loss starting from theta I, and then you just interpolate between these 2 points, and you get your next initialization theta+1. And you keep doing this till you have seen the n tasks, and then you output the final initialization that you have.
Should I think of taking many steps of gradient descent, or like almost to completion, or how many, like when you say GD, like how many steps should I think of taking?
Right. So like if I'm describing the algorithm reptile as in their paper, this can kind of be any operation. It can be like, let's say, stochastic gradient descent or some variant which uses Adam or something like that. But later on, I'll describe when I need it, I'll describe what exactly this will be, like mathematically.
Cool, thanks.
Okay, and now again, as I described earlier, the way we're going to use this initialization is run some gradient-based algorithm starting from this initialization on the empirical loss or some variant of it. And the two, so we'll be mainly interested in two algorithms, and I'll describe them now. So the first one is what I call regularized gradient descent. So it's for simplicity, I'm going to say this algorithm will run gradient flow till convergence on the regularized empirical loss starting from this initialization theta in it that was meta learned. And this is the empirical loss, which is with the regularization term. And the second one is just running gradient descent for t steps with some learning rate eta on the empirical loss. And again, you start from theta event. So these are the two algorithms for which we would be showing guarantees and upper bounds and lower bounds, etc. And note that other algorithms like maybe stochastic gradient descent, one pass SGD is, at least in the convex case, it's more very similar to this regularized gradient descent algorithm. Okay, so now with this framework, I'm going to describe the existing guarantees for convex losses. And by that I mean this function L for every point Z is going to be convex in the parameters theta. And we also assume it's going to be G Lipschitz, which is the assumption that, like, this is the assumption from prior work basically. And of course, this is not true for neural nets, but if you do have convex losses, then you can show guarantees when, so suppose you have some theta bar that has norm upper bound by D, but the average distance of this theta bar from the optimal parameters for different tasks is upper bounded by some quantity V. So in this figure, you can see that this theta bar has norm upper bounded by D, but there is a ball of radius V around it, let's say of Euclidean ball, that contains most of the optimal parameters for different of the tasks in the distribution mu. And if you have such a setting, then so now this is a very so this is a result from multiple papers from last year, and just a disclaimer that this is a very lossy summary of the results, and they show results for slightly different settings for different algorithms, etc. But the essence is the following: that you can say that the excess risk for using the initialization learned by Reptile on, let's say, the regularized gradient descent objective will have excess risk upper bounded by this, where again the important quantity for us here is this GV divided by square root n. But essentially, this is saying that if you had okay, so now basically with this theorem you can see the benefit of doing meta learning, which is if the inter-task parameter distance V is much smaller than the norm of the parameters, then there is actually a benefit in doing meta learning, because now you're suffering GV over square root n rather than GD over square root n for a new task. And in our work, we actually show that that without any more assumptions apart from convexity and Lipschitzness, this sample complexity of GV over square root n it's almost tight. In other words, you can actually construct a meta learning instance with certain specific convex losses for which you can show that a new task will require these many samples. Yeah, so any questions about the existing convex results? Okay, so good. Yeah, so now, so from the convex case, we see that it actually captures the intuition that we want to learn an initialization that's close to the task parameters, and it's done in either the Euclidean distance sense, or there are other variants in those papers that I cited there, which do it for other notions of distances as well. The question is, can this provide insight into meta learning with neural networks, let's say? And the natural first step for us would be to maybe look at neural nets in the NTK regime. That is when in the limit of the width of the networks going to infinity. And here we can basically treat neural networks like as a kernel, and a task is now just a linear regression problem in the NTK feature space. So roughly your prediction is going to be linear in the parameters and these features phi of x. And the loss, so the risk for a task is just going to be how far away are you from this optimal prediction y star for the task t. But in this setting of linear regression, learning a common theta bar is basically the same as learning a common regressor y bar, because you have a linear function. You're just trying to learn a common function y bar, And the task, and then the goal for a new task is just to learn the residual, which is the actual prediction minus this common prediction that you're learning, which is independent of the task. And if you think about it, this kind of makes sense for certain problems where, let's say for any given X, across different tasks, your prediction is actually hovering around a certain common value. And for each task, it's like only slightly deviating from this common value. For example, this is an actual data set. If you want to predict the exam score for a student, given a feature agent for the student, and different tasks could correspond to different schools, maybe there is an inherent score for each student that they would get. And for different schools, because they have different difficulty levels and different settings, you would have some variations across the schools. However, this common predictor does not really make sense for standard meta-learning test benches. So the first example is that of the sine wave dataset, where the different tasks are learning, all tasks are learning a sine function, but they have different periodicities and different biases. So the A and the B are different. And across these tasks, the average value of y of x across the task is basically going to be 0. Because for every sine ax, you also have a sine minus ax. And similarly for plus b, you have a minus b as a task. So on average, you're just learning to predict 0. So learning a common predictor is not going to help you in any way, because you will just learn the common predictor, which is 0 for every x. Similarly, in the other test bench, a popular test bench of this average k-wise tasks, where you take a data set like mini ImageNet, let's say, which has around 200 classes, let's say dogs, cats, etc. And the inputs are images. And every task is a classification problem with 5 randomly sampled classes from these 200 classes. In this, you have the issue of label shuffling. So if you have a task which is separating dogs, cats, and horses, let's say, you're equally likely to have any permutation of the 3 classes as the first class, second class, or the third class. So task 1 and task 2 have equal probability, and so does every permutation of dog, cat, and horse. And now for a given image X, for the first task, the prediction is 1, 0, 0, but the second task is going to be 0, 0, 1. If you think of doing regression with the one hot encoding. Oh, sorry. And then the average prediction across all tasks is basically just going to be 1/3 for every X. So learning a common regressor is not helping you. You're just going to learn this fixed bias of 1/3 across for every X. And so if you think of the linear regression problem, you see that learning a common regressor should not help you. However, we know that neural networks are successful at solving these kind of tasks in practice much better than doing single task learning. So clearly the NTK regime is not sufficient to explain the success of neural networks. Hopefully this example is convincing enough. So why are they successful in the first place? And I would argue that they're successful because this is something that Andre also alluded to earlier, which is they learn good representations at the penultimate layer. In fact, there is empirical work also showing that most of the power of like method like MAML can be derived by fixing the first L-1 layers for a new task and just learning a linear classifier for a new task. And then the question is, can convex analysis actually capture this notion of task similarity, that is existence of good representations? And in this work, this is the problem that we're studying. So what we do is we construct a simple meta-learning instance that captures one-dimensional linear representation learning. And in the convex formulation of linear regression, we show that no initialization-based meta-learning method can succeed, in the sense that you will always suffer a sample complexity of at least d over epsilon. However, in the non-convex but equally expressive formulation of two-layer linear network, the Reptile procedure that I described earlier will have a new task sample complexity of just 1 over epsilon. So you lose the dependence on the dimension. And as far as you know, this is the first analysis of initialization-based method in the non-convex setting. And it actually requires us to look deep into the dynamics of this specific gradient descent algorithms that will show up in each of these. And you can show that it actually learns the subspace structure, and hence you lose the dependence on the dimension.
Nikunj, just to make sure I understand, so like this
Yep.
Raghu et al. Paper, the point is, I guess, that if you run something like MAML, and let's say you get a good initializer for all but the last layer, and then when you get a new task, you just train the last layer, so just the linear layer.
Right.
That's basically like you get most of the performance. That's what the I'm interpreting it correctly, right? That's
yes, that's exactly
okay.
that's exactly what it is. Yeah.
Okay, cool.
Okay. Yeah. So now I'll describe this meta-learning instance that we constructed. It's very simple actually. And then I'll describe the lower bound for the linear regression and then the upper bound for two-layer linear networks, two-layer linear networks. And we'll see how much of the proofs we can get into. Okay, so we are interested in regression where input is d-dimensional and output is a scalar. And the two regressor functions that we're interested in is either linear function, just have W transpose X, where W is the parameters and X is input. Or you have a two-layer linear network where we're going to refer to A as the first layer and W as the second layer. And A is a D cross D matrix. So there is no restriction in the dimension of the output of the first layer. And hence, both of these are equally expressive. And now I describe a task. So each task is parameterized by a vector in RD, V. And the distribution for this task is, the input distribution is just standard Gaussian. So it's zero mean and covariance identity. While the label is basically going to be the linear function W transpose X, but with some Gaussian noise or with variance sigma square added to it. We don't really need this to be Gaussian for any of the settings. We just need the variance to be sigma square and Y to be independent of, and independence in the Y across X's, but let's say it's Gaussian for simplicity. And then as defined earlier, the loss for this task, which is parameterized by V, is just the squared error loss between the prediction and the actual prediction Y. And the distribution over tasks, mu, is defined as uniform distribution over just two tasks, T of W star and T of minus W star, for some unknown but fixed vector W star. And then the excess risk can be simplified to something like this, where you first sample a task, which is same as sampling a sign, plus or minus 1, and then sampling a data set and then measuring the error of the risk that your algorithm incurs, minus the sigma square. So the sigma square here is the R star, which is the optimal risk that one could hope to ever achieve. And that the sigma square you suffer is because you have noisy labels with variance sigma square. And importantly, note that all the tasks in mu, which is basically the two tasks in mu, the predictions only depend on the projection of X in the direction of W star. So if you know that projection, that's sufficient to get basically zero risk or sigma square risk. And for simplicity, we assume that the norm of W star and sigma are both some constant R. This is just to make the signal and the noise of the same order. This is, and also for simplicity of presentation. Okay, so now that we, so any questions about the setup, the meta-learning instance? Okay, cool. So now I'll describe the lower bound for linear regression. So now, as I said, the prediction is just linear in W, and for the distribution of the tasks that are defined, the excess risk is just, it's going to be just the difference in the prediction of the algorithm minus the actual classifier, the true classifier, which is S of W star. It's either going to be plus or minus. And recall that the algorithms of interest are going to be either running gradient flow on this regularized loss, or running T steps of gradient descent with some fixed eta. Okay, so the lower bound, the statement says that any meta-learning algorithm that uses any number of training tasks and any number of samples per training task cannot learn an initialization that's going to be very good if the initialization is going to be used by one of the following algorithms for a new task. And by not very good, I define this new task sample complexity, which is basically for any algorithm, it's the smallest value of n for which the excess risk can be made smaller than epsilon. And yeah, so the theorem is that for any initialization W, the minimum sample complexity of any initialization is going to be d r square over epsilon. Recall that r is the norm of W star and the noise sigma. So this says that if you use W star for a new task for either doing gradient descent or regularized gradient descent, you still need d r square over epsilon squared regardless of the initialization. And no matter how you pick the regularization parameter, or no matter how many steps you do for a new task, or what's the learning rate for a new task. Yep. So any questions, comments about the... Okay.
Sorry, so maybe like one quick question. So to
Sure.
try to relate, I guess, to the previous setup where you had these like capital N samples from the distribution over tasks. So
Right.
I guess like how did that vanish in this case?
So it doesn't vanish. So this is a lower bound. So it says that it's at least going to be this, and it says that no matter how many training tasks you have.
I see. So how, no matter how many like
yeah, so you can have access, right?
Okay.
Yeah, to infinite training tasks, infinite samples per training task.
I see.
But if you are restricted in the way that initialization-based meta-learning restricts you, which is learning an initialization and using it in one of these gradient-based algorithms, then you have to suffer this sample complexity.
Okay.
And the proof is actually, oh, I'm sorry. Yeah, the proof is not that complicated, and like the result is also not that surprising if you think about it for some time. So I'll just give the proof for the case where we use regularized gradient descent with a non-zero lambda, and in this case, actually, the objective that you're doing gradient descent over is basically strongly convex and has a unique minimizer. So regardless of what initialization W0 you learn, you're going to just gradient flow or descent will just converge to that unique minimizer. So it's going to be independent of the initialization. And now the initialization doesn't help you in any way. So you're just going to suffer the lower bound of doing linear regression, basically, without any additional knowledge. And it's believable that is basically dr square over epsilon. And in the other cases, it's a little more involved, but it's still, the idea is very simple. So you can, for other cases, you can basically write the solution for t steps of gradient descent and learning rate eta. You can write the closed form solution and the dependence on the initialization W0. And it's actually just a linear dependence.
Sorry, can I just ask a clarifying question?
Sure.
So it looks like the theorem that you're saying, even though you're like sort of stating it in the context of meta-learning, it doesn't actually have to do with meta-learning. It's kind of just saying that no matter where you start, the expected risk over the distribution of tasks is still going to be this, like you're going to suffer this sample complexity. Yeah,
that's exactly right. And it's actually not a very surprising statement as well. Like if I tell the statement to you, it's like, it's not very difficult to prove. Like it's not a, the way meta-learning comes into the picture is the fact that initialization-based meta-learning methods imposes restriction that all you can do is summarize the training task into this initialization and just use this initialization as in some gradient-based algorithms. That's the only way meta-learning comes into the picture.
And I guess the point is the best, since it's symmetric around zero, like your best starting point is basically just zero, right? Like so,
yeah, that's
okay.
But you do, that's exactly the intuition. But you do need that to restrict the way in which you're going to use the initialization. Like if I just encoded information about the task, like learned the one-dimensional subspace and encoded it in W0 somehow and then decoded it and done something, then of course you can reduce the sample complexity. Yeah, the idea is just that these gradient-based algorithms are just going to learn a final solution that's linear in this W0. And hence the best initialization ends up just being the zero initialization.
And I guess that this is like nice enough for the version where you have eta and t's that the solution after t steps, like it's just, I guess every gradient step is something linear, so you can just write down the explicit formula. Is that what the?
Yes,
like,
that's
okay.
exactly it. Yeah.
Okay.
And so note that the MAML method exactly does this. It wants to do few gradient steps and hope that you are doing well. But like what happens is when you, for different steps and different etas, they're basically going to have a trade-off between the bias term and the variance term. So if you take very few steps, your bias is going to be large, your variance is going to be small. And if you reach the end, then yeah, variance is what is going to kill you. Okay, so yeah, so to conclude, like in the convex case, these initialization-based meta-learning methods cannot learn the underlying structure, which is learning this one-dimensional subspace. And that's because of the restriction that these methods impose. On the contrary, we'll show that for two-linear and linear networks, Reptile updates can actually learn to project the data on that one-dimensional subspace and hence reduce the sample complexity by a factor of t, at least. Okay, so yeah, I'll describe the two-layer case now. So again, it's the same setup. The regressor is now W transpose AX instead, and you can exactly rewrite the excess risk depending on the first layer and the second layer learned by this algorithm. So it's again the effective prediction of the classifier, effective classifier basically of the first and second layer minus the true classifier. And the algorithm of interest here is the way we're going to use an initialization is we fix the first layer and we just update the second layer. But we run, again, as before, we run gradient descent till convergence on the regularized loss. But here now we fix the first layer and we only do gradient descent on the second layer. And in principle, it should not be very different if you update both layers actually. But just for simplicity of analysis, we just analyze it for this case. Right. And the Reptile algorithm that we're going to assume that Reptile gets access to the population, gets population access to capital N tasks. That is, it exactly knows the distribution for those tasks, and it does the usual updates that the new initialization is going to interpolate between the current initialization and the output of gradient descent from the current initialization on the new task. And unlike in the convex case, the output of gradient descent for this two-layer linear network is heavily depends on the initialization. And that is, in some sense, that is going to be exploited. As opposed to the convex case where the output, especially if you have a strongly convex loss, is not going to depend on the initialization at all. And note that the assumption that you have population access to the N tasks, capital N tasks, is quite strong. However, the lower bound for convex case holds even in this case. And even though there are other trivial algorithms that could actually just use population access to these tasks and do something very in a simple way. The whole point of this is to show that the updates done the Reptile actually learn the subspace. Yeah, so any questions about this setup? Okay. Oh, I see somebody raised their hand.
Yeah, that was me. Sorry. I have a question. So in the convex case, if you had somehow the structure is that the two optimal W's are like W star and minus W star.
Right.
If the selection of optimal W's for all your tasks formed the convex set, then would you not have had a problem? So it's just that the two W stars form a very non-convex set. If they were instead a fairly convex collection of W stars, so either they're like a little ball around one of the W stars, or somehow, like if I just took all the tasks, took all the W stars and put them together and they formed a convex set, if in that case, would your first method break?
So going back to the convex case, yes, it will break. Even if you have, let's say, the W stars are distributed in a Gaussian distribution on a subspace, let's say, or yeah, like on a one-dimensional subspace or like two-dimensional subspace, let's say it's a circle or something, it's still going to break. And the idea is again the same, is that the average of the W stars is basically 0. So no initialization in some sense is going to help you better than the 0 initialization.
I see.
Yeah. So yeah, and this W star and minus W star is not that artificial as well, because the examples that I gave as motivation essentially
The
had
label
this issue.
shuffling thing.
Yeah, the label shuffling and the sign example. Yes.
I see. Okay, thank you.
Yeah. Okay. So now, yeah. So given this algorithm for the downstream task, the upper bound basically says the following: that suppose an comma wn is the initialization learned by Reptile after seeing n tasks. For large enough number of tasks, but still like not that large, and small enough kappa for some good balance between the number of tasks and the kappa. So kappa here is sorry. So I need Reptile to start with this initialization, which is the first layer is initialized as kappa times identity, and second is initialized as 0. And I'll get to different initializations maybe in the like discussions later. For small enough kappa and for large enough n, you can show that the sample complexity for a new task using this algorithm is just r square over epsilon for an appropriate choice of the regularizer like this parameter. And again, contrasting it with linear regression, the lower bound was d r square over epsilon, so it's a factor of d better as expected. And now I'll try to give like a proof sketch that covers most of the important ideas here. So recall that this is the Reptile update. You start with kappa identity and 0, and then you do this interpolation steps. So the first observation is that the Reptile updates always satisfy this property, which is the AI, capital AI, the first layer is going to be some scalar times W star transpose plus kappa times identity. And the second layer is always going to be some in the direction of W star basically. And I'm going to call these kinds of first layer and second, these kinds of A and W as good A and W. I don't really have any meaning assigned to good here. I'm just calling them good A and W. And we're going to prove this by induction by actually using the following lemma, which is the lemma essentially says that if you are starting with a good A and W at any point I, and you look at the solution found by gradient flow on the new task, which is S of W star. So you look at this solution. So it turns out that the solution is also going to give you good A and W. So if you start with good A and W, doing gradient descent on this objective, you'll end up with a good A and W. And then by induction, you can see that after you do the interpolation updates, the interpolation is also going to be a good A and W. And so you're always going to have good A's and W's. And more specifically, the solution that you find is going to depend on both A, B, and the sign, that whether you had plus W star or minus W star. It's going to be a function of A, B, and S. So it's a function of the initialization. And this is actually proved by looking at the dynamics for deep linear network, dynamics of gradient descent for deep linear network. That was first done by Andrew Sachs and colleagues in 2014, and later was made robust and analyzed also for gradient descent in 2019. But
somehow
this is...
is somehow the intuition here that everything just kind of ends up, the eigenspaces are kind of aligned, and you do some kind of like everything just kind of decouples along the diagonal? So
right.
That kind of, okay.
Yeah, that's the intuition. And that's the reason why I need the specific initializations of identity, etc.
Yep, got it.
Yeah, and yeah, so the closed form solutions only exist for very specific initializations, which is exactly what you said, which is the eigenspaces aligning with the W star that you want to learn. And I'll get back to a discussion about this at the end. Okay, so the important points here are that even for, you want every good initialization to satisfy A greater than B. That your first layer should have a higher component of W star than the second layer. And this is actually going to show up later, that this is crucial. Okay, so now I did describe to you what these functions f and g are, and I'm going to show you what they look like. So you can just combine the two lemmas and see that the dynamics for the matrix is just going to be summarized by these two equations here, where the AI is, this interpolation between the F and the AI. And similarly, B is an interpolation between G and BI, where F and G are these complicated looking functions. And so right now you don't need to focus on the exact expressions for F and G, but an important point to note is that the sign of the W star, that whether it was plus W star or minus W star, is always picked up only in the G function and not in the F function. So F is independent of S actually. So the first layer is always positively going to update the W star direction, whereas the second layer picks up whether it was W star or minus W star. And this is also going to be crucial in the analysis later. And importantly, this happens because of the initialization of A greater than B. Okay, so now I'm just going to rewrite, like the entire dynamics of Reptile can just be summarized to these equations basically. That you have some AIs and BIs that are updated in this interpolation fashion, where the AI bar is this complicated function F and G basically. And now I'm just going to try to give some intuition for what this dynamics looks like. So if you actually run this dynamics and plot things, so first importantly, you see that it satisfies these two properties, that the product of, oh, I'm sorry, there's a typo here. So all of these are AI bars and BI bars here. Sorry, but the right hand side is just AI. So AI bars and BI bars satisfy that the product of AI bar and BI bar is going to be the sign. Just assume R is 1 for now. It's just going to be the sign plus or minus 1. And it satisfies that the A square minus B square is the same as the initialization A square minus B square. So this is a property of that gradient descent gives you. And if you try to plot this, so suppose you are at a particular AI and BI here, you know that the solution that gradient descent will find will satisfy these two properties. So it should satisfy, let's say S is minus 1 now. It should satisfy that the product of AI bar and BI bar should be minus 1. So it's going to either lie on this segment or this segment here. But you also know that it should lie on this hyperbola, I believe, which is, it should have the product, this difference A square minus B square is actually an invariant for gradient descent. So it should also lie on this curve. So it's going to lie on the intersection of these two curves. And so it's going to be this point here. And then you do this interpolation update. Oh. And so using this exact dynamics, you can show the following two properties, that AI is always an increasing sequence. And BI on the other hand is going to hover around the mean value of 0. So by mean value, I mean in the randomness of the sequence of the signs that you see, the SIs. I'm going to make this more formal later, but any questions about this updates or how it fits into the proof? Okay. Hopefully I've not lost you with these equations. Okay, but what you can essentially show that even though you know that AI is an increasing sequence, you don't want it to stop at a particular value and convert somewhere. And you can actually show that if by picking the right interpolation parameter, which depends on the number of tasks, optimally, you can show that AN is always, AN can always be made an increasing function of capital N. So AN at the end will satisfy this property, that it's going to be as large as the number of tasks to the 1 over 6. And now, so the key insight is that you have your first layer, which is always increasing its component in the direction of W star transpose. And the question is, why should this help you? And it's because if you have an A that is something like this, where the component of W star transpose is extremely large, you essentially have almost a rank 1 matrix. And this matrix is just going to project your data onto the subspace of W star in this direction of W star. And once you do that projection, effectively now your task has been reduced to a one-dimensional linear regression problem. And so the sample complexity is just going to be the sample complexity of, which is basically going to be constant because the effective dimension is just 1. So it's going to be R square over epsilon. And now, because you don't exactly have a rank 1 matrix, you can handle the small deviation from this rank 1ness by choosing an appropriate regularization parameter lambda when you're doing your ridge regression for your new task. Yeah, that's basically the intuition. And that's essentially going to be the end of the proof sketch. So let me know if you have any questions.
I guess like here somehow the win comes from the fact that you know that once you've figured out what the what the right subspace is, once you've like figured out like double transpose, then you're basically done. Like then it's just like a one-dimensional whatever linear regression problem. I guess like when you have like a deeper net or something, you're trying to like you would be trying to find some kind of more complicated manifold, I suppose. Like if you're thinking of like having some kind of like class of tasks on top of the like penultimate layer or something as a representation.
Right. So I haven't done the calculation exactly, but I believe that for deep linear networks at least, if you again fix the initializations to be appropriate enough that, let's say, everything except the last layer is of the same scale or something, then you can probably show that all layers basically update only in this direction, in this subspace.
I see.
Using again dynamics of like linear networks.
Right.
Like gradient descent on that. And then essentially effectively you're learning the subspace and then, yeah. Right. Okay, so we see that in this setting, running Reptile in the non-convex setting of like two-layer linear network is like a factor D better than in the convex setting. And this happens again because you have two layers and the first layer can learn the subspace, as Andre was saying. Whereas in the convex case, you can just learn an initialization and that doesn't give you a lot of information. And you can actually show similar results, not just for the Reptile updates, but also for a standard representation learning objective, where you learn a common first layer for the training task and different second layers for different tasks. And you don't need to add any regularization or anything. You can just show that gradient descent on this objective. It will also give you a first layer that learns a subspace. And I'll just point out that meta-learning in the case of linear representations, which is exactly this problem of two-layer linear network, has been studied in the past, and there is like some very recent work as well. But they analyze it for very specific kind of algorithms that are tailored for this particular problem, and they don't analyze it for like initialization-based meta-learning methods like Reptile. And also these algorithms use some explicit regularization, or they restrict the first layer to have an output dimension of k, with a smaller output dimension than the original input dimension. So they explicitly restrict you to learn low dimensional representations in the first layer. Whereas this analysis shows that gradient descent can automatically learn the subspace. You don't need to restrict it. You can start with a D cross D matrix and initialize it with like scalar times identity, and it will learn the subspace automatically. And so now, so now in terms of future directions, our analysis actually heavily depends on the dynamics of gradient flow and linear networks. As it was pointed out earlier, that these analyses are very sensitive to the initialization, which is you need the spectrum of the initialization to align with the spectrum of the W stars, the eigenspaces, to align. And because of this reason, when we try to analyze it, so we wanted to actually analyze this for the more general case of learning a k-dimensional subspace. Even though one-dimensional is enough to show the separation between convex and non-convex. But learning a k-dimensional subspace where the tasks are now W star sampled from, let's say, Gaussian on the subspace, because of this restriction, it's kind of not trivial to extend the analysis to that case. And even extending it to, let's say, a first layer which is not necessarily has like D hidden units. Maybe it could have like M hidden units and random initialization. And all of these things cannot be handled right now, even though there is no fundamental reason that you cannot handle this. And even experimentally, you see that you can actually, the first layer actually learns the k-dimensional subspace, even if you have a k-dimensional subspace or you start with random initialization. So these kind of things happen experimentally. It's just that analysis, the tools that we have are restricted. And also, of course, you must have noticed that the assumptions about the data distributions are kind of somewhat unrealistic, that you have same input distribution for all tasks and you have access to population loss. But even in this case, even with these assumptions, it was kind of non-trivial to show that these methods can learn the subspace. And to go beyond these assumptions, I don't think there's a morally any, the main bottleneck is actually having a robust analysis for dynamics of linear networks. So as I said earlier, there exists a robust analysis, but that suffers a very bad blow up. So it says that if you run if you start with a epsilon bad initialization, which is not the ideal, but epsilon away from the ideal initialization, after t steps of gradient descent, that initialization blows up as e to the t square. And this is really bad blow up. So we'll perhaps need like a better analysis for linear networks in order to go beyond that. And of course, the question is whether this can say anything about neural networks in any regime. It's not clear, but we know that just looking at NTK and linear regression is not enough. But perhaps there is a way to extend these kind of ideas to neural networks as well. And again, like maybe trying to show analysis for methods other than Reptile, like the mammal method, which is very popular as well. And maybe we also need to go beyond just initialization-based meta-learning methods. Maybe these methods work well right now for the current data sets, but maybe the current data sets are not strong enough. That could be the case. But yeah, so these are like the future directions and questions to think about. And yeah, that's the end. Let me know if you have questions. Thanks.
Sure, I'll go with one more. So I guess to some extent, there's kind of two things that one could try to decouple here, right? So one question is whether there exists a good initializer, or what kinds of, I guess, assumptions on the subsequent tasks make it such that there is a good initializer that you can take one or two gradient steps or whatever that gives you something good. And the other one is, can you find it with something like mammal or something else? So I guess like, have people tried to at least look at the existential version of the question to some extent?
So in the convex case, people have done this in the form of this distance metrics, and in some norm. In the non-convex case, there basically does not exist any there did not exist any sample complexity analysis in any non-convex setting. And in the convex case, most of the ones that I have seen are based on some notion of distance, either Euclidean or some Bregman divergence, something like that. So yeah, I think that's the extent of like the current state as far as I know.
Right. Though I guess presumably, like if you push all measures of complexity into the metric, presumably you could also do something like that for the non-convex case, except that probably the metric is just going to be something super nasty.
Let's see, is that a fair statement to make? I mean, ideally you would want a metric that's also, you want multiple properties, and it's hard to get everything, but you want it to be interpretable, you want it to make sense. Maybe you want it to be testable in some sense. Yeah. So, I mean, one metric is just whether or not a method like mammal works well in practice. And yeah, so it's not clear at what level of, how fine-grained you want your assumptions to be, and what exactly do you want it to be testable in some sense. I guess the empirical paper that did the representation learning kind of did answer this question, that all you need is a good representation. You don't maybe necessarily need to update the representation.
I see.
So it at least answers it in that sense. But I agree that especially I think that there like experiments can actually help with getting more insights in this. I definitely think so.
So is it like, I guess, have people tried to compare the representations that you get from something like mammal with other representation learning methods? Did you kind of check how much better versus worse you get?
It's a good question. I don't have an answer to that question. I don't know if somebody in the audience has. I haven't seen anything like that.
Hi, Misha here. In general, I think mammal representations and like reptile representations are possibly not as good as representations learned that target things like downstream just linear classification. So there's a popular alternative method to MAML called protonets, which basically just learns the representation such that like the centroid classifier is a good downstream classifier on a like task-specific classifier. And those on the very specific task of like few-shot learning for images, those seem to work better. What MAML and these types of methods are good at are possibly things like language modeling and so on, which is perhaps less representation-based. But yeah, so I would say that MAML representations are perhaps not as good as others. But then you have to like learn, like have very complicated methods of learning these representations that themselves need to be analyzed.
And I like, are the gaps sort of substantial? I guess if you check some kind of downstream, like training a linear classifier for downstream tasks for vision or something, like are the gaps very large?
There's some very recent papers that show, I think they're getting to be fairly large gaps, yeah. So like you can learn a representation that will, such that linear classification over it will do much better than any initialization, than like a MAML initialization.
Cool.
But I guess there's another thing that's not clear to me, which is like in all the places that people use something like MAML and it works well, I think all of them are basically function approximators, and you can always phrase that as some representation learning. Like you can always split your function as a representation and some linear function over it, and then do some representation learning based method on that. And I don't actually know if these kind of experiments are done and whether these are as good as MAML or better or worse. I don't really have the answer to this question. I don't know if Misha has seen something like this. But I haven't seen it.
Yeah, I agree. I guess my answer is more along the lines of people are comparing representations learned by MAML, but you still update the entire network, versus representations learned by protonets or some other method, where you do a very simple like linear classifier or centroid classifier on top of the representation. Right. The reason why this might still be, so the algorithm, like the with-it task algorithms are different. The reason that why it still might be relevant is, I guess, the Raghu paper, right, where they do run the experiment of just training the last layer, and just training the last layer does do slightly worse than training the entire network. So there's like a sequence of inequalities suggesting that the representation might be worse.
Cool.
Right.
Any other questions for Nikunj? I guess that was it then. Thanks so much, Nikunj. It was a pleasure having you.
Yeah, thanks for inviting me. Yeah, this was a good
Thank you.
experience. Yeah,
thanks for everybody who stopped by. I'll see you next week.